Jump! Oh, sorry, just kidding. That's a different, that's a discontinuity. I remembered what I was talking about. Okay, so a couple of things is if the limit is unbounded, in other words, it's just getting bigger and bigger or smaller and smaller, or it's going to infinity, then there has to be a vertical asymptote there. Duh. And if the limit on the left, remember that's the little minus sign, and the limit on the right, that's the positive side, don't equal, then there's a non-removable jump. And then if the limit as we approach c of f of x does not actually equal the stated y value, then there happens to be a hole or a gap. And if you go back, all those examples I just gave you match up with all of that. And then some properties about continuity, keeping in mind that b is just a number, some constant, is that if I have two continuous functions and I add them together or I subtract them, that's still continuous. If I take a continuous function and I multiply by a coefficient, it's still continuous. If I take two continuous functions and I multiply them together, still continuous. If I divide them, still continuous. And if I compose them doing f of g of x, that's also still continuous. So many rules. So on this next, on the intermediate value theorem, which is very, very important, what it says is this. So I have this continuous curve, f of x, and it's continuous on the closed interval a to b, so from a to b, here we are, and k is some number in between their y values. So here's k, and it's in between the two y values. So f of a, f of b, those are the y values. And so what it says is, since it's continuous, there has to be some number between a and b that has that y value. That's what intermediate value theorem says. So you have to know that. And then these are just some types of functions that are always continuous. So polynomial functions, those are things like your quadratics and your cubics and your degree 4s and so forth. Rational functions, of course the denominator can't equal 0. Radical functions and trig functions. So every point that's in their domain, remember, this isn't continuous everywhere, but it's continuous at every point in the domain. Same thing here, it's not continuous everywhere, it's not all reals, but it is continuous at every point in their domain. So if I want to figure out all the x values where it's continuous, I notice that it's going to negative infinity here, positive infinity here, but it's nice and smooth and continuous everywhere else. So the domain values is everything except 0, so I'm not defined as I get closer and closer to 0. So my domain values would be negative infinity to 0, and then 0 to positive infinity. So this is just going to start to help your recognition of functions that are continuous and then ones that are not. So on the first one, in letter A, I have a cubic. So that one's continuous everywhere because they have a nice continuous, one of those S-type curves. I'm sure you all remember them. And of course, I could put this into the graphing calculator to convince myself, but it'll be doing something like this. And then letter B, I can factor the denominator, and of course those are going to be no-no numbers, so x cannot be 1 or negative 1, and if you remember on these rational polynomials, that's going to give me vertical asymptotes. Which are non-removable. So the non-removable discontinuities are at plus and minus 1. And so of course on letter C, I can factor again, and when I cross this out, remember, I get a hole. So that will be a removable one, and then I'll have 1 over x plus 3. That's going to give me an asymptote, a vertical asymptote, which is non-removable. And I'll see you in the next video to write it down.